So, hi again, and I'm back with you with my second video, and we're looking at voltage converter. As you can see there on the board, just below the differential equation, you see that there's a single phase system and Booth's voltage converter on the left. Okay, so without further ado, we will move on to our real deal, and we'll get this thing going. Okay, so we're going to explain what we have there, and we look at the function where we have dx by dt equal to the function g of x of t. So hi again, and we going through what we have here, and we make discussions, etc., and look at some of the things that we have. Well, we still have that function that I mentioned in the last time, which is still here. Now we have the equation. This is called a state space differential equation. I didn't write it there, but that's what it is, a state space. Based upon I represent two states. So we could have we could have put I over here. It doesn't matter, just put it here. I is equal to 1, 2. Yeah. This circuit have its continuous conduction mode circuit, and so it's not the discontinuous mode circuit at all. So this one, it's the Boost voltage converter. It's supply voltage, and inductor. This is basically the resistance of the inductor here. It's got a diode. This represents a transistor. It can be a MOSFET, fast switching MOSFET. What type of MOSFET are we talking about? We're not the PNP, but the NPN. That's fast switching. The PNP is it's a slow version of transistor in terms of switching speed. So most of when you're doing your design in a voltage converter, especially if it's belong to the classical converter. So within the classical, for the classical voltage converter, there are basically three classicals. We have what is called, we have the boost. One of the first one is we call, there's a buck as a classical, and the other classical is this boost converter, and the third classical is that we call the inverter. I'm putting all caps here, basically keep it real. The inverter. So what we have there is the boost converter. So we're looking at the second one. So another day we'll look at both the buck and the inverter, and we'll do the characteristics of these systems. I'm a specialist in designing these, and I've done a lot of them, and the algorithm for them know very well how it's done. The feedback, which is called the control law, for this regulates the entire system, which basically allows the pulse width to have various sizes. So it modulates, so it mimics. And the equation for that, which is a triangular wave, which is generated by a small equation here. Not sure if you can see it well. It is a small equation where it is written as, this is to generate the triangular wave, a very simple equation we use is, especially in the simulation, this A represents the frequency, the value of the frequency. E represent the floor value. This equation actually can give you that triangular wave. So to get the height of what you want, you're going to have to multiply the result of this by some number. Let's some variable p, whatever p is, and that will give you your t, your triangular wave output, that with the height. P represents a constant value. T is the time over the distance of the switching. So what we'll do, what I'm going to do today, we're going to look through this basic explanation from the differential section, the function here. This is what we have. And we're looking at the single system. This is a circuit layout. This is actually a feedback. We have the transistor, the load, and the filter. All of these converters carry out what we call states. So they can be what we call the on state or the off state, or a state that is in the discontinuous system, which most of these what I'll be doing is strictly the continuous conduction mode system. And I will also get, when I go to the discontinuous, then I will show you another thing with there that is concerned. So what we're looking at here is the circuit itself, the arrangement, the feedback control, how it's arranged, control law, what is inside here. This basically relates the difference between this one and what's on the output to get this signal here, right? So K is basically a constant, and it actually regulates what we have here. It's already have the difference here, but this is another function, basically another constant that regulates the value of the output. That is integrated here in the control law. So what happens here, it finds the difference between this and that. So whenever there's a particular difference, you get a particular switching, right? And what is inside here are a set of operation amplifiers. They're the one who actually, for comparator, they actually evaluate the difference between this signal and the feedback signal to give you this level of pulse. So wherever the feedback signal intersect with the triangular wave, the difference there give us the pulse. And that pulse is what controls this transistor. And it switches on and off based upon the width that is given. The voltage here is approximately 15 volts because these transistors, they're open, anything over 5.5 volts. Anything under that, it may not open. So here we assume that the switching here is at least 15 volts. We definitely know. And that's coming from our what? Operation amplifier, right? Which is the comparator. And that actually switches our transistor and regulate the circuit. So when this is closed, there's our energy generates in this section. While this, what happens is once this transistor is on the on state, what we have here is this current flows, right? That end up creating what? That end up creating a reverse current in the diode. So what happened to the diode become an open switch, and nothing flows in this direction. So the circuit literally induce an energy, and that actually create an issue with the diode. So it's not in the forward bias, it's in the what? The reverse bias. So the diode is, when this diode is in reverse bias, it's open. So this circuit, what happened here now is that the capacitor now is behaving similar, the same behavior as the inductor. Energy is being transferred to the load from the capacitor, because the capacitor is a storer and the inductor is a storer. Both elements are considered nonlinear. So this system is not a linear system, but when we making a calculation, we have to linearize the calculation to get approximated result, which actually gives us the result of how the circuit behavior. The circuit itself, when we look at it, we have two states. We have the on state. So the on state is when this switch is closed. This is what it looks like. Energy is generated within the circuit, while this one also is reducing energy, giving energy to the system. So that is when the circuit is closed. When the circuit is open, we end up with this off state. So we consider this to be the on state and this to be the off state. What the off state does now, the energy from here also stored in the disk and also feeds the system as well. So this is basically the circuit arrangement. And what the circuit arrangement does, if these are properly optimized, where you have your filter, the load, the inductor, if everything is in a balanced state, then you will get good results. You will have this, you will have your pulse width modulation operating as necessary as possible. The output for this resembles this shape, where this would be your output voltage, Vout, which is greater than Vin. Vin could be, this would be an estimate of Vin, where there's a difference for this one, right? So what we have here is that the output greater than the input, hence boost voltage converter. So we get a boost voltage converter based upon the input. So once the output itself here, whatever value, when you use your voltmeter, the voltmeter will tell you if it's greater than the input voltage. And that is due to the basic function of the entire circuit. When everything is in harmony, balanced, where your control law works in very well, your frequency of this is able to switch this at a rapid rate. I recommend, for even some of you, students, recommend always go for make at least 50K. Okay, that's basically 50K. That's the frequency, right? 50K. That will allow the switch here to switch as as rapidly as possible, to allow energy to be stored in the inductor, transferred to the capacitor, the filter capacitor itself, which is the energy storage. They're both energy storage. Stored in different ways. The graphical form, when this one is discharging, this one is storing. When this one is discharging, this one is storing. So they do it in a vice versa manner. They're both non-linear, so they make the system complicated. These circuits works in various ways. We can vary this to see the varying output here. So, but there's a time in this circuit that this cannot be varied no more. Maybe when this reached to let's say 60 volts, there are some issues with the circuit itself, right? And that affects the output, and also affects the feedback itself, where the system is no longer able to to do any more switching. Okay, now this is the equation that we basically developed from the state, and we have the on state. This is what it is. This is a 4x4 matrix. B represent a column matrix, which is this, where X is basically a column matrix, where you can have it in reverse. You can have the current here. This is the inductor current. We can have it in the reverse form, where the inductor can be at the top, or it doesn't matter. I like to have my voltage considered at the top, and and the current, the inductor current, at the bottom. Right. What else? Here we have, now we need to look at the switching property, which is the pulse modulated. This is shows the difference between the pulse. These are never the same. With the PWM, they always varies, because it mimics what goes on with the feedback because of the inductor, changes within the inductor. So it is not as smooth as it may look here. You know, it's a bit of ripple. The ripple effect on this resembles something like that. That's what it looks like. Okay? And why it looks like that is because of the energy change and transformation between these two elements within the circuit. And that allows this smooth line, this is what it looks like when it's magnified to a certain degree. This is what you see for this smooth line here on the output, right? There are various things here on the board. There's a lot of things here on the board. The next step, what I'll be doing is to show the calculations for this based upon the circuit itself, and we'll continue. So today, what have we done today? Very quick look at the boost converter. And we looked at the circuit itself. We looked at the control law. Inside here is basically the difference between these two, as I mentioned earlier on, right? And that allows the switching the pulse width modulator to keep this on and off, on and off. And you generate these states. First state, second state, where B, which is a matrix, column matrix, is the same, B1 is the same as B2 in this case for the boost converter. In the other converters that I had here, the classical, especially the buck, these are not the same, right? They varies. Both A and B varies in a different mathematical order. The width of the pulse has to do with the total time. So from T0 to T2 is called a periodic time. So, and it repeats itself. So as it repeats itself, the circuit take this stage, take that stage, and it come back to this one, and so on, and it constant. Every time it switches, it's what we call create these pulse stages, and it switch between state, between off state, on state, on state, off state, and so on and so on. And as it goes and goes, it steadies off. This is a bit of overshoot on the system, because as this generate energy in the initial stage, the switching needs to switch either have the pulse, either the width is wide or narrow, so it varies until it stabilizes. Once it stabilizes, you get this nice smooth constant output, which is considered the steady state of the system. But there's an issue with the circuit because they're actually nonlinear in nature, in themselves. They're considered nonlinear, right? The steady state, for it to achieve steady state, is at infinity, we would say. So we just considered that it acquires steady state once the voltage became stable approximately in a stable state. That's what it is, approximately in a stable state. Control systems without this, just the ordinary circuits, without these nonlinear elements, then we can acquire steady state in simulation, where if you use in MATLAB, you will be able to see the steady state. It doesn't matter whether it's MATLAB or it's a SPICE program. You can acquire steady state, or what else? We've got a lot of simulated program out there, PSpice or PSim. Who else? MatCAD. All of these, they are able to simulate your circuit or your whatever circuit design you have with various elements. If you have nonlinear elements in it, then it, acquiring steady state, it will relatively acquire a relative state that we consider to be steady. But in reality, it's not. It just varies between very small variations, very, very small changes. Okay. I hope I've said enough, and we'll be doing some more. The next stage is to solve this equation, and we will show the calculus side of it. I will put the integration of this, how it's been, how when you have this, what it should be look like in integration form, and then the solution of the integration, what it should look like. The whole idea here is that for university students, it doesn't matter whether you're undergrad or master's, PhD, you actually write down, you actually go ahead and solve the whole idea is when you have a certain state, you follow the general rule or principle. There's no need to be pondering how we acquire certain states. It's just simple method to get to your final equation. But the integration part of this is really, really not necessary because of the transition state. When it's in the transition state, it's not needed. We really need it to be what the calculation in the steady state, right? So the transition state is in the integration calculation, which is really, really not necessary. We need the final state, and that basically comes, we estimate it to be over this section. So we could consider this part to be the transient, right? The transient state, and over here we consider it to be the steady. Okay, over the transient, over this side until it reaches a certain. We just decide where is it transient and where would it be in the steady. So really, the result that we would need from this is really the steady state, where this is basically what averaging the system. So we'll average out the system and get an approximated result that actually will be the mathematical model of this entire circuit. All these circuits can be mathematically modeled to another level. Depends on whatever it is. We can write a mathematical algorithm for this. Where all of this, on a practical sense, can be simulated. Build a circuit and run it. You get this result. You can also do it mathematically and get the same result. Right? And where in MATLAB, you can simulate this. You can write the algorithm notations in M files and run run one file as one will be the program file, the other one would be the parameter files. So the parameter would have these values in it for this, and that, these loads. This one basically would be a bunch of numbers that will actually a certain function, example for k, where it will actually reduce the value of the output voltage for us to create our input, our feedback signal. So this circuit it's really regulated for it to be stable. It needs a feedback, and no feedback, it means an open circuit. So this one is considered a closed circuit. So for open circuit circumstances, then there's no feedback. So it's something that's controlled and switched. It means that there's no regulation on this. So whatever happens to it, it cannot be controlled so that the thing can function properly. So in all electronics devices or whatever, domestic electronics or industrial or commercial or military or aerospace, it has to be in control. Definitely control. Everything has to be regulated to make it energy efficient and to boost and improve on efficiency. Efficiency with anything that we're using today has to be efficient enough so that it uses energy that is whatever energy is using, efficient enough for it to be have any good warranty use and not energy waste. Energy is very expensive to be created and be used. So there you go, there you have it. I have been doing a little bit of explanation on these circuits. There's other people on YouTube, but I'm going to do something here that none of them doing. There are a few professors there, they're doing some good work. What I'm going to show you guys how to really solve these differential equation to another state that I've not seen on YouTube. There's this system here can have an equation that when you solve this mathematically, you will simulate it in right there. This the exact formula within MATLAB and simulate it, and you will get the result exactly the same as how the circuit is performing, and how the circuit itself is performing. And this basically, in comparison, you will know that your mathematical model is the same as the real circuit or your simulated circuit. So it's a matter of comparison. But what the good thing with this is that you can do certain things with this that you're not able to do with this. You can make changes within the mathematical model to the input value to see what happens to this here and the output. And then you can compare, you can get what we call a phase diagram. What is the phase diagram? The phase diagram is comparing the current, both comparing the inductor current and the output voltage. You get a certain shape on your graphical, the characteristics, how it looks. And there's a certain stage where you iterate this through Newton's method. What it does, it finds certain values, and it will give you, every time you take a sample, it will record a sample, and that will give you a certain state for your equation, what it's doing. So you will have, by doing all of that, you will end up having a section where you will see the system basically steady, and then another part of the system is not steady. Something happened, you know, a particular phenomena. These are very complicated circuits. They look simple, but they're not. When you really understand them, you really get to work. You really get to know how to get them steady, have them in a steady state quickly. The key here is to find the most suitable control law to effectively drive this transistor. That's the correct word in engineering. To drive is a transistor being driven, and what it does, it allows this to absorb the right amount of energy to send to this circuit. And then sometimes I see some other developers, they make this filter quite large, and it's not necessary. You don't have to be large. It means that their control law is not of any substantial optimized. It's not optimized enough so that you can reduce the size of this to get the most out of your circuit. So once the control law is done properly, it will generate the right pulse width for driving the transistor for it to have an effective circuit, and you can have a proper boost output voltage that you may require. So it has to do with how your control law has been done. Okay, I hope you enjoy that, and I looking forward to see you guys again, and I hope that this has enlightened you a little bit. A lot of things on the board anyway, but bear with me. We get there. Okay, so yeah, we will look at first. We will solve this one. In the meantime, every day by day, I'll make sure we do steps for this. So the next time I'll be just putting the differential equation for the two states, solve it, work it down with show you how to use the Jacobian matrix, including with the Newton's method, and some other things we'll look at. Excuse me. Throughout that, we'll work it on the two stages. So for now, I won't be looking at the discontinuous. And normally, it's mostly work with the buck converter. So when we start with the buck, we look at the various stages of the buck. The buck is used in basically all electronics devices that we have. A lot of electronics devices using buck converter. This one is basically mostly used for solar systems, battery chargers, etc. All right. Thanks for tuning in, and Happy New Year, everyone, and have a good one. Bye. Wow.